Hey Math 137, what's up? In this video we're going to be taking a closer look at graphs of trig functions. This is information from section 6.3 in our textbook. Some of the tools that we're going to be needing in this discussion, well, actually one of them comes from 6.4. We're going to be using our unit circle, which you can kind of see below there. We introduced that picture in section 6.4. We did talk about the values earlier than that. We're also going to be using our theorem on repeat values for some of our justification here. So we're going to first focus on the three primary trig functions: sine, cosine, and tangent, and then look at their reciprocals afterwards. So first, let's look at the graph of sine. So we got our unit circle here. We're going to be working with radians. Whenever we're doing functions of real numbers, we need to be thinking about radian mode when we're referring to our unit circle or anything involving angles. And so let's go ahead and get some of these points, these input values, marked along our x-axis. So here we're going to be looking at the graph of y equals sine of x. Maybe I can go with the thinner pen here. Okay, so let's see, between 0 and pi over 2, notice that we have our x-axis marked off in multiples of pi over 2. Each pi over 2 gets cut in half. So I'm just going to go up to 2 pi. So it gets cut in half at pi over 4. 3 pi over 4. 5 pi over 4. And 7 pi over 4. And then it also gets cut into thirds. And I'm not going to label these because it's going to get a little bit too cluttered. But each pi over 2 interval gets cut into thirds as well. At pi over 6, pi over 3, 2 pi over 3, 5 pi over 6, etc. Now along our y-axis, our values here for sine, remember we're looking at the y components of the points. We have 4 primary values, 0 and 1. Those are easy to identify. We've got 1/2 along the y-axis is one that we need to identify. And then root 2 over 2, that is approximately 0.7. And root 3 over 2 is approximately 0.8. So we can get those marked. We got 0.5. I think 0.7 would probably be about right here. So we'll call that root 2 over 2, and then 0.8 would be right there, 0.3 over 2. All right, so in this first quadrant, the first quadrant along our unit circle, that corresponds to the interval 0 to pi over 2 along our x-axis here at pi over 6. Sine of pi over, or sorry, I guess starting at 0. Sine of 0 is 0. The y component for the angle 0 radians, the y component of the point corresponding to that angle is 0. At pi over 6, the y coordinate of the point that corresponds to pi over 6 is 1/2. So at pi over 6, we're at 1/2. At pi over 4, the y coordinate of the point corresponding to pi over 4 is root 2 over 2. So we'll plot that point. At pi over 3, for x equals pi over 3, the y coordinate of the point that corresponds to x equals pi over 3 is root 3 over 2. So we can plot that. And then at pi over 2, the y coordinate of the point that corresponds to pi over 2 is 1. I'm going to get this point moved just a little bit. Want the speed nice and smooth. All right, so on that interval, the graph of y equals sine x if we kind of connect the dots in a nice smooth fashion, looks like that. Between pi over 2 and pi, let's see, at 2 pi over 3, that's our next tick mark. The y coordinate is root 3 over 2, so we start to go back down. At 3 pi over 4, the y coordinate is root 2 over 2. So we're going to continue to go down here. The next tick mark here would be at 5 pi over 6. The y coordinate is 1/2. And then when our input is pi, the angle is pi, the point that corresponds to pi, the y coordinate of that point is 0. So we're back down to the x-axis. All right, focusing on the interval now from pi to 3 pi over 2, we have some different y outputs. We have negative 1/2 now. And negative root 2 over 2. And negative root 3 over 2. Right, so the next angle, the next tick mark up corresponds to the angle 7 pi over 6. The y coordinate there is negative 1/2. At 5 pi over 4, the point that corresponds to the angle 5 pi over 4 has y coordinate negative root 2 over 2. Get that point plotted. The next tick mark corresponds to the angle 4 pi over 3. The y coordinate of the point that corresponds to 4 pi over 3 is negative root 3 over 2. And then finally, when we get to the angle 3 pi over 2, the y coordinate of the point that corresponds to the angle 3 pi over 2 is negative 1. We're down here kind of at the bottom of the unit circle. And then very quickly, I think you guys can probably see how this is going. When we move between 3 pi over 2 and 2 pi, we get the following points that we can plot. And we go connect the dots. And we see this familiar sine wave. This is what when people talk about a sine wave, this is roughly the shape that they're talking about. All right, so that constitutes one period of the function y equals sine of x, or I actually prefer using function notation rather than y equals. So I'm going to call this f of x equals sine x, if I can get my pen out. So that's one period of the graph of that function. Now here's where we use our theorem on repeat values. Can I just copy this whole thing? I think I can. I'm going to go ahead and do that. We got the benefits of technology here. I'm going to go ahead and copy this whole thing. Ow. Is it going to let me drag the whole thing? Let's see, undo. Paste it again. I don't think it's going to let me drag the whole thing. Oh well, that was going to be fun, but then it wasn't. I'll just do it by hand. When we go to do the next 2 pi, now I like to focus on the zeros and the ones. Okay, so we start at 0. After 2 pi, I go up to 1 here. So on the first pi over 2, I go up to 1. On the next pi over 2, I go back down to 0. Over the next pi over 2, I go down to negative 1. And then over the next pi over 2, go back up to 0. So when I'm drawing graphs of sine and cosine in particular, I like to find where those zeros and ones are. And then I know the rough shape of the wave that goes in the middle. Don't plot the points in the middle. After this first time plotting them, we don't need to plot them anymore. We could also get rid of this unit circle now. We don't need that. Go back the other way. So now the zero is kind of at the end of a period. At the end of our period, we go back down to -1. If we're going to go backwards, back down to -1. I don't know what happened there. Go back down to -1. As I keep moving to the left, I go back up to 0. As I move to the left, I go up to 1. And then back down to the start of our period, back down to 0. Right, and then the in-betweens look roughly the same here. Okay, so there's our graph of f of x equals sine of x. Now, ultimately, your goal, we don't want to be plotting too many points. All right, we plotted these points here to convince ourselves of the rough shape of this graph. But when it comes time to getting these pictures drawn, again, I think you're really focused more on the overall shape, the fact that this is a wave shape, our peaks and valleys are important points. The x-intercepts are important points. These points here in the middle are not quite as important. All right, let's go look at the graph of cosine of x now. We have a lot of the same values that show up for cosine, just in maybe slightly different spots. So the input values are going to be the same. We have all of our pi over 4s, pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. Also all of our pi over 6s. We get pi over 6, 2 pi over 6, which is the same as pi over 3. 4 pi over 6, which is 2 pi over 3, 5 pi over 6, and so on and so forth. So all of our input values are going to be the same angles here. And the output values, we have positive 1/2. Maybe I'll label my pi over 6s this time. Pi over 6, pi over 3, 2 pi over 3, 5 pi over 6. So I'm getting lost here. 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. Get those labeled on this picture. On the y-axis, we've got 1/2. We have root 2 over 2 and root 3 over 2, along with negative 1/2, negative root 2 over 2, and negative root 3 over 2. Okay. We can start to plot points. Now cosine at 0, we're looking at the x-coordinates of all these points now. Cosine, when our angle equals 0, or when our input equals 0, the x-coordinate of the corresponding point is 1. So we start off at 1 here. At pi over 6, we move down to 3 pi over 2. At pi over 4, we go down to root 2 over 2, move around to pi over 3, we're at 1/2, and then around to pi over 2, at the angle pi over 2, the point that corresponds to pi over 2, the x-coordinate is 0. Remember, for our definition of the trig functions of real numbers, we're looking at the x and y coordinates of these points, and cosine corresponds to the x-coordinate. So the x-coordinate of the point that corresponds to pi over 2 is 0. That means that when we're drawing the graph of cosine of x, f of pi over 2 is 0. As we continue around, now at the angle 2 pi over 3, the x-coordinate, the corresponding point, is negative 1/2, so we're going to continue to go down here. At 3 pi over 4, the x-coordinate of the corresponding point is negative root 2 over 2. And at 5 pi over 6, the x-coordinate of the corresponding point is negative root 3 over 2. And then when our input is pi, the point that corresponds to an angle of pi, the x-coordinate there is negative 1. So here we've got a half period of points to plot. And if I connect those dots, something that looks like this. The other half period, we could plot the points. We could plot, again, we're looking at the x-coordinates of these corresponding points. The angles here, the radian angles, will be our inputs, and x-coordinates of the corresponding points will be our outputs. And if we were to plot those points, I'll just plot them quickly. We would get something that looks like this. And then connect those dots to get, again, now we have one full period of the graph of cosine of x. Now, I think we're done with our unit circle now. Possibly. I'll keep it around just in case. Now, again, just like we did with sine of x, we could use our theorem on repeat values to say that for the next full period, from 2 pi to 4 pi, the graph just copies itself. We start off at the top here and drop down to 0 over the next 2 pi, and then drop down to negative 1 over the next, over the next pi over 2. So we drop down to 0 over the first pi over 2, drop down to negative 1 over the next pi over 2, back up to 0 over the next pi over 2, and then up to 1 over the last pi over 2. So we get another full period of our graph of cosine. And we could go back. Now I guess I could, instead of starting at the end like I did with sine, I could start back at the beginning at negative 2 pi. I think of the period of cosine as starting at 1, and then the next point go down to 0, the next point down to negative 1, back up to 0, back up to 1, and then connect not with lines but with these nice curves. Well, that one was looking really good. Oh yeah, I really like that. Okay. So ultimately, if we were to get rid of all of the grid lines, our graphs for sine and cosine look very similar. Right? They both have this wavy motion. It's just that cosine, they kind of start at different points. All right. A couple ways of thinking about it. If you think about the beginning of the sine period, I think of it as starting at 0, whereas the cosine period starts at 1. Or you could think of the cosine, if you take this sine graph and kind of shift it to the left, pi over 2, you end up with the cosine graph. So if you remember doing some graph transformation stuff in Math 136, now think about what a shift to the left corresponds to. That might end up being one of our trig identities here in a little bit. Okay, there's our graphs for sine and cosine. When it comes to looking at the graph for tangent, that's our next challenge here. We're going to use a fundamental identity. The fact that tangent of x is equal to sine of x over cosine of x. Thinking about this it's not really a rational function, but we're going to use maybe some of the tools that you learned about when you studied rational functions in Math 136. In particular, one of the things that you learned about graphs of rational functions is that when the denominator of a rational function is equal to 0, that often tells you, not always, so I'm going to put this in sometimes. When your denominator of a rational function is 0, you sometimes get vertical asymptotes. All right. Now, the sometimes here, if your numerator also happens to be 0, then that's where you got to do a little bit more work. If your denominator is 0 and your numerator is not 0, then you always get a vertical asymptote. That's not what I wanted. I wanted an eraser. You always get a vertical asymptote. So we just kind of saw the fact that our sine and cosine graphs they had the same shape, but they were different. One is shifted a different way. The point being that wherever cosine is 0, sine is going to be a different number. All right, or you could think, I guess I'm glad we looked at our unit circle. Think about it another way. The point 0, 0 is not on the unit circle, and therefore sine can never be 0 at the same time as cosine. It's another way of thinking about that. The point being that, all right, for this fraction, whenever our denominator is 0, the numerator is not going to be 0, and that's where we're going to get our vertical asymptote. So we want to look and see where cosine is equal to 0. So referring to the graph of cosine, we see that cosine is equal to 0 to 3 pi over 2. That means that the graph of tangent is going to have a vertical asymptote there. Similarly, at negative pi over 2, we're going to have a vertical asymptote here for tangent because cosine is 0 there and sine is not 0. Also at pi over 2, we have a 0 on the graph of cosine at pi over 2. So we will have a vertical asymptote in the graph of tangent. And then the last few, we got 3 pi over 2, 5 pi over 2, and 7 pi over 2. The graph of cosine has a 0 there. And that means that the graph of tangent is going to have a vertical asymptote. Okay, so that's the first step of getting the graph of tangent, the graph of tangent of x drawn, is to get those asymptotes drawn in. Then also, I guess another thing that we learned about rational expressions in Math 136 is that if the numerator is equal to 0 and the denominator is non-zero, then you get that the expression is equal to 0. Right? So I can plot my x-intercepts for tangent by looking at sine. Wherever sine is 0, cosine's not going to be 0 because again they're never 0 at the same time. And tangent will be 0 there. Tangent will also have an x-intercept. So thinking about the x-intercepts of sine, we have it at negative 2 pi, pi, 0, pi, 2 pi, 3 pi, all the multiples of pi. All the multiples of pi, that's where sine is 0. That's where the numerator of this expression will be 0, and therefore tangent will also be 0. So we can plot some zeros here at all of the multiples of pi. All right, now last little step here for getting tangent drawn, I think we will use the unit circle again here. This is one that's maybe a little bit challenging. We're gonna see some notation that you might not be familiar with, and I'm not gonna make you use this notation, but this is just the notation that our textbook uses. I want to focus on the interval 0 to 2 pi now. All right. As I move from x equals 0 to x equals pi over 2. All right, the input. We start at 0, and then we're looking at what happens as I get closer and closer to pi over 2. So we're thinking about when this is the notation here, as x gets closer to pi over 2 with x less than pi over 2. All right. What's happening now? We're thinking about again, tangent. Tangent is being equal to sine over cosine. It's one of those fundamental identities. All right. The numerator here, the sine values are getting closer to 1. The denominator, those values are getting closer to 0, and the denominator is positive. And we're looking at the first quadrant here in our unit circle. All of the x values here, all the x coordinates of the points along this circle, positive x values. So two things: the fact that sine and cosine are both positive in the first quadrant, that means that tangent's going to be positive in the first quadrant, or on the interval 0 to pi over 2 here, tangent's going to be positive. And furthermore, the fact that my numerator's getting close to 1 and my denominator's getting close to 0, that's the part that says that tangent is growing very large. Here's the notation. Use this arrow notation. Tangent goes to infinity. That's the notation that we use. Say that tangent is getting very large and positive. All right, so that's kind of the behavior near that part of the asymptote. And if you wanted to plot some points, I think one of the points that we could plot is at pi over 4. Sine and cosine, the x and y coordinates of the point that corresponds to pi over 4 is the same. So I guess we could plot that point. It's going to make drawing this graph a little bit harder. All right, so in the first quadrant, I don't like any of these pictures. Oops. On the interval 0 to pi over 2, the graph of tangent looks something like this. Now I want to go back and focus on, well, I guess let's go ahead and continue on around the unit circle from pi over 2 to pi. All right, so now we're thinking about x is getting close to pi over 2 again, but now x is larger than pi over 2. All right, what happens when I get close to this asymptote from the right side? All right, so now x is going to be larger than pi over 2, or x is going to be in between. Our input value for our function is going to be in between pi over 2 and pi. That means that we're in the second quadrant. Now, as I get closer and closer to pi over 2 in this quadrant over here on the unit circle, my x values, or cosine, still gets close to 0, and sine still gets close to 1, so that still holds. But now all of the points that correspond to these values, the x coordinates of those points are negative. So that changes. Cosine is negative. So now in the second quadrant, sine is positive, cosine is negative. I have a positive number divided by a negative number. That means that tangent is going to be negative. And when I get close to pi over 2, the numerator is close to 1, the denominator is close to 0. That means that the fraction is very large but negative in this case. So tangent goes to minus infinity when I approach pi over 2 from the other side. So as x gets closer and closer to pi over 2 with x bigger than pi over 2, since tangent is negative and the numerator is close to 1 and the denominator is close to 0, tangent's going to be getting very big and negative. And so on the right side of this asymptote, we're going to be going down to negative infinity, or very low on the graph here. So between pi over 2 and pi, our graph is going to look something like this. And we could use some similar arguments to show that between pi and 3 pi over 2, the graph looks like this. Again, in the third quadrant, now both sine and cosine are negative, so tangent's going to be positive on that interval. And then finally, in the fourth quadrant, between 3 pi over 2 and 2 pi, sine and cosine have the opposite sign. In this case, cosine is positive and sine is negative, which means that tangent is going to be negative. Okay, so now this is not what we would consider a period for tangent. Actually, tangent, we discussed this very briefly in class, tangent is pi periodic. It's got a period of pi. It repeats itself every pi. And the period for tangent that we focus on is the period between negative pi over 2 and pi over 2. So this is the piece that gets copied. You can see that that's what our graph looks like between pi over 2 and 3 pi over 2. If we were to finish the graph between 2 pi and 5 pi over 2, we would see that completed period. So this single in between each pair of vertical asymptotes, we have one period of the graph of tangent. And we can finish all the rest of the periods here. Now, one period of the graph of the tangent kind of looks like a cubic. If you remember drawing the graph of y equals x cubed, kind of got that cubic shape. It's not exactly that, but it's close enough to where it's okay for you to think of each period of the graph of tangent as having a cubic shape. All right, so there's the three graphs of our three primary trig functions, sine of x, cosine of x, and tangent of x. To get the other three pictures, we're going to be using some reciprocal identities. So let's go look at sine of x. The reciprocal of sine of x is cosecant. So if I look at g of x here, let's get our skinny pen. G of x equals cosecant of x. Remember, cosecant is the reciprocal of sine. And using some ideas, I'm not gonna focus as much on the details here as I did with tangent, focusing on some of the ideas that we had when we drew the graph of tangent. We have a fractional expression here, 1 over sine of x. Wherever that denominator is 0, we're going to have a vertical asymptote. So wherever the graph of sine is 0, the graph of secant is going to have a vertical asymptote. So at 2 pi, at pi, at 0, we have a vertical asymptote here. at pi, all the multiples of pi. All right, so the graph of cosecant is going to have those vertical asymptotes. Now, wherever sine is 1, cosecant is also going to be 1. 1 over 1 is equal to 1. So we can plot some of the points, some of those points for cosecant here. Wherever sine is equal to 1, cosecant is going to be 1. Wherever sine is equal to -1, cosecant is going to be -1. 1 divided by -1 is -1. And then thinking as the reciprocal, for instance, looking at 0 as x gets close to 0 with x greater than 0. So we're thinking about being on this interval pi over 2. We're getting closer to 0 here. Our fraction, 1 over sine of x, or cosecant of x, is positive. Since sine of x is positive, we can see the red graph here is above the x-axis, so sine of x is positive there. 1 over sine of x, that means cosecant is positive. The denominator is going to 0. Which means that the fraction, since the fraction is positive and the denominator is going to 0, that means that cosecant is going to infinity. We're up here. Same thing as we get close to as we get close to pi, continuing on, as x gets closer to pi, sine of x is still positive. That means that 1 over sine of x is still positive. As x gets close to pi, sine of x is getting close to 0, which means the reciprocal is getting very big. As I guess this is a relationship between numbers and their reciprocals. If a number is small, or if a number is close to 0, then its reciprocal is very large, and vice versa. So thinking about cosecant as the reciprocal of sine, wherever sine is small, cosecant is going to be very large. Wherever sine is close to 1, the reciprocal is also going to be close to 1. So that's what the graph of cosecant looks like on the interval 0 to pi. On the interval pi to 2 pi, sine of x is negative. We're below the x-axis here, which means that cosecant is also going to be negative. We still have this reciprocal relationship, though, where when the red graph gets close to 0, its reciprocal graph gets very large, although in this case large and negative. Okay, so the blue graph that we've drawn so far, that is one period of the graph of cosecant. If I shift over to pi, we'll get another period of the graph of cosecant. Did not draw these asymptotes in very nicely. That's okay. These graphs don't have to be perfect. It's the ideas that are the most important. If we shift our period to the left, 2 pi, then we get a third period. So between -2 pi and 4 pi here, we get 3 full periods of the graph of cosecant of x. We could use some similar ideas to get the graph of secant of x. Remember, secant is the reciprocal of cosine. Sorry, not cosecant, but secant. Secant is the reciprocal of cosine. So if I look at the zeros on the graph of cosine, I could draw some asymptotes, some vertical asymptotes for secant, wherever the graph of cosine goes through the x-axis. the graph of secant will have a vertical asymptote. I accidentally switched pins there. Switched to my rainbow pin. And then just like we did with sine, you know, each, I guess, in between each pair of vertical asymptotes, the graph of cosine is either always positive or always negative. And we can attach these, I guess I call them like the secant. There's like the cosine humps, we're going to have like the opposite secant humps. So where the graph of cosine is positive, we're going to have this secant. It's kind of like a parabola. It's not a parabola, but just like with the tangent things you can think of as cubic looking. You can think of the pieces in between the asymptotes for secant and cosecant as looking kind of like parabolas. But I'm just attaching these kind of opposite humps. The cosine hump goes from 0 to 1 back down to 0, or from 0 to -1 back up to 0. The opposite hump, the secant hump, goes from infinity to 1 back up to infinity, or from -infinity up to -1 back down to -infinity. All right, a couple more here. And there is the graph of secant. So whenever I am drawing the graph of cosecant or secant, I really do think about the graph of sine or cosine, get those graphs drawn in, and then just kind of draw in the opposite humps. Get my asymptotes drawn in where the graphs go through 0, and then get kind of the opposite humps going. One more graph. We have the graph of cotangent. That is the reciprocal of tangent. So wherever the graph of tangent goes through the x-axis, cotangent is going to have an asymptote. Or you can think of, since tangent, you could think of another way of thinking about this, is that tangent is cosine over sine. And so wherever sine is 0, cotangent is going to have a vertical asymptote. I accidentally clicked on my eraser there. Now this one's maybe a little bit harder to see than the humps, the opposite humps that we had for secant and cosecant. So let's take this somewhat slow. So we're looking at the reciprocal of the red graph. So wherever the red graph gets close to 0, the blue graph is going to be close to either plus infinity or minus infinity. And we have to think about the sign here. So for instance, over here by -2 pi, just on the right side of -2 pi, the red graph is getting close to 0, and it's positive. That means its reciprocal graph will be getting close to positive infinity. And then as we move through the interval -2 pi to 3 pi over 2, the red graph gets very large and positive. Its reciprocal will get close to 0. So we're going, as we get closer and closer to -3 pi over 2, the blue graph will get closer and closer to 0. Now it's not necessarily, we don't want to go writing this stuff down, but it's okay to think about this. 1 divided by infinity. If you think about infinity as just, shorthand for a really, really big number. 1 divided by a really, really big number is a really small number. And so 1 divided by infinity, like the reciprocal of infinity, should be 0. Now if you don't like to think about those kinds of things, that's okay. I don't like to think about those things all the time myself, but there we go. All right, now from negative 3 pi over 2 to pi, we're kind of continuing this reciprocal trend. We're looking at the reciprocal of the red graph. So right on the other side of negative 3 pi over 2, the red graph is very big and negative, which means that the blue graph, as its reciprocal, will be very small and negative. And then as we get closer to negative pi, the red graph is getting very small and negative, which means that its reciprocal will be very large and negative. And so we're going to approach that asymptote that way. So each period, now that's, I just drew one full period of the cotangent function there. Each period of the cotangent function will look exactly the same. We'll just copy it over. It goes from large and positive down through 0 down to large and negative. So large and positive down through 0 down to large and negative. Start off large and positive down through 0, large and negative. So it's kind of like the opposite. It's kind of like a negative cubic shape. If you think of tangent as having a positive cubic shape, then cotangent should have a negative cubic shape. Now this one got a little bit busier than, we're able to think about the graphs of cosecant and sine in the same spot, or the graphs of secant and cosine in the same spot. Thinking about the graphs of tangent and cotangent in the same spot, it gets a little bit busy. And so you can, and I often do, kind of like we thought of tangent as sine over cosine, we could think of cotangent as cosine over sine, using that identity, and say, all right, wherever sine is 0, so at the multiples of pi, 0, pi, 2 pi, 3 pi, 4 pi, all the multiples of pi, we're going to have these zeros in the denominator, so that's where we're going to have our vertical asymptotes. Wherever cosine is 0, so those are at all the odd pi over 2s, pi over 2, 3 pi over 2, 5 pi over 2. That's where we're going to have zeros on the graph of cotangent. And you could do this kind of the SIGN sine analysis. All right, in the first quadrant, we're thinking about these as ratio. Both the numerator and the denominator are going to be positive. So between 0 and pi over 2, my graph wants to be positive. In the second quadrant, my coordinate points have opposite SIGN sign. So I have, in this case, a negative divided by a positive, cosine divided by sine. That's going to make the graph of cotangent be negative. That's usually the way that I think about it personally. All right, we're going to be working more with these graphs in an upcoming section. So make sure that you get the basic graphs nailed down, the basic shapes, the locations of the zeros and the asymptotes and things like that, or the thought process. Even if you don't necessarily memorize all of those things, you definitely need to have the zeros of sine and cosine memorized. All right, this unit circle, it's very important that you have as much of this memorized as you can, but especially the zeros. I call it the 4 corners of the unit circle, even though there aren't corners. The multiples of pi over 2, 2 pi over 2, 3 pi over 2, and so on and so forth. Like those 4 points are the most important points by far. So you definitely want to know those. But being able to work from the known zeros of sine and cosine to the graphs of sine and cosine, and then from there the graphs of tangent and cotangent and the reciprocals, secant and cosecant. That's going to be something that, you make sure that you work through that thought process yourself a few times so that you can recreate those thoughts, not just memorize the steps for getting the picture drawn, but the thought process. You're not necessarily memorizing the thought process. You're just doing the thought process repeatedly until you understand the thought process and can recreate that on your own. All right, that'll do it for this lesson. If you have any questions, please let me know. Thanks for watching.